Hi, today going to the PAT paper from 2010, looking at questions 12 through 16. These are the first 5 multiple choice questions. So question 12 says we have 2 radioactive elements, A and B, and they have half-lives of 8,000 and 16,000 years respectively. If they start in a proportion of 1 to 1, what is the proportion after 16,000 years? Okay, well, let's just say arbitrarily that there are n of each. Okay, so after 0 years, we have n of A and n of B. What about after 8,000 years? Well, A has had 1 half-life, so that's going to have halved. But B hasn't had a half-life yet, so that's still got n. And what about 16,000 years? Well, again, A's had another half-life, so that gives you n over 4. But B has now also had a half-life, so that gives you n over 2. So we see that the proportion is going to be n over 4 to n over 2, which is 1 to 2. So question 13, we're told 2 resistors, R1 and R2, of resistance R1 and R2 are connected in series with a potential difference V across them. And we're asked to find the power dissipated in R1. So let's draw this out. So they're in series, so you have R1 and we have R2, and we have a voltage potential difference V across them. We're going to lose some voltage V1 across R1 and V2 across R2. And we know the way potential dividers work is that V1 will be equal to the fractional resistance R1 offers of the two. And we know they're in series, so we know that R total, let's write that here, R total is simply R1 plus R2. So the fraction that R1 has is in fact R1 over R1 plus R2, and it's that times V. So that's the fraction of V that R1 gets. Okay, and we know that power is V squared over R. So this tells us that power that is dissipated across R1, P sub 1, is V1 squared over R1, which is R1 squared, V squared, over R1 plus R2 squared times 1 over R1, which comes out to give us V squared R1 over R1 plus R2 all squared. So in question 14, we're told that a mass of 100 kilograms lies on a 2 meter log, plank of wood, at a distance 0.5 meters from the end. And a builder tries to lift up the other end of the plank here, and we'll ask what force is required to lift it from NB. Well, let's label on the forces on our diagram here. So we have clearly the weight force, 100 G, and he's going to lift it here with some force F. Now what we're going to do is we're think about moments about the end here, because the moment about this point here is where he'll be pivoting around. So as the builder lifts up the end of the log, that's the end that will stay on the floor, so that's what we're going to pivot around. So we'll do anti-clockwise and clockwise. So anti-clockwise is, well, the only force downwards is the weight. So that's 100 times G, 10, times its distance, 0.5, which gives us 500 Newton meters. And then anti-clockwise, well, it's going to be the only force upwards, F, times its distance, 2 meters. So that's 2F Newton meters. And then he's going to pick them up, we want them to be equal. So we're going to have 500 is equal to 2F, which tells us that the builder must apply 250 newtons of force. So in question 15, we're told that according to a plane, it flies in the northwest direction at a speed of 141 kilometers an hour. But it flies into a wind that flies directly from north to south at a speed of 100 kilometers per hour. And we're asked to find what is the actual speed and path, so direction, that the plane goes relative to the ground. Well, let's go at this in terms of vectors. So we have some vector going, first of all, let's draw our compass on. So we have our northwest, northeast, southwest, obviously. So we have that it's going directly northwest. We have some vector here, which is of magnitude 141. That's going from north to south. And then we have, in the northwest direction. So that's the speed of the plane. Then we have some other vector going exactly from north to south of magnitude 100 kilometers an hour. That's the speed of the wind. And we want to find the net result of these two vectors to give you the actual path and speed that the plane will travel at. Now let's think about this. So let's imagine we drew this on a graph. So let's draw a graph out, right? So we have some axis, x and y. So we know that our plane is this vector here. That's going exactly from in the northwest direction. So for every 1 it moves here, it's going to move 1 here. So we can actually label that with some vector which goes -1 in the x and 1 in the y. Okay, and similarly we have the wind. Well, that's going exactly from north to south. So that's going from every 1, it goes down in the y direction, it goes 0 in the x direction. So that has direction 0, -1. And then we simply add them. So the net vector is equal to, well, -1, 1, plus 0, -1, which has direction -1, 0. So that corresponds to moving in this direction here. So we see it's going to be moving south. And what's the magnitude of that? Well, clearly we now have a right angle triangle, so this is exactly here. So we have that our speed v will be equal to the square root of 141 squared minus 100 squared, which is 100. So it goes at 100 kilometers per hour. Sorry, I don't know why I called this south. It's to the west, obviously, because clearly it's going from right to left. So that's in the west direction. So it's 100 kilometers per hour west. So in question 16, we're told that a teacher wants to listen to his favourite radio station. And this radio station has a frequency of 1000 kilohertz. But his radio only shows the wavelength. And I'll ask what wavelengths must he tune his radio to tune into this station? I.e., what wavelength does this station have? Okay, well we know that it's a radio wave, so it's light. So we now have speed c. Speed c, 3 times 10 to the 8 meters per second. We also know c is f lambda, and therefore lambda is c over f, which is 3 times 10 to the 8 divided by the frequency, 1000 times 10 to the 3, which is 3 times 10 to the 5 over 1 times 10 to the 3, which gives us a wavelength of 300 meters.